First, I'd like to thank the organizers for having invited me to this wonderful colloquium. I really enjoy being here. I'll talk about causal inference. I talk about an aspect of big data, and the aspect involves heterogeneity. And I'd like to acknowledge my main collaborators for this talk, Jonas Peters from the MPI in Tübingen and Nikolai Meinshausen from ETH Zurich. I had an earlier title actually on the webpage, and that's the motivation in a way for the research I'm doing. I'd like to achieve the goal to design new perturbation experiments for large-scale biological systems. So that's kind of the underlying goal, and I use some sort of causal machinery in order to make improvements towards that goal. So the goal in genomics, this is where I have exposure, this is where I have collaborations, is the question, if we would make an intervention at a single or at many genes, what would be its effect on a phenotype, on a response variable of interest? And I'm using the subjunctive here because I want to predict these effects without actually doing the intervention. So classically, this would be maybe from observational data, observation from a steady-state system, or what is more the focus today here in this talk, it's maybe observational and interventional data, maybe with known specified interventions, or I also go a step further when we have maybe changing environments or different experimental settings where the intervention is not so exactly specified. Maybe it's only vaguely specified or even unspecified. So we've heard in the morning, my goal is also a what if I do question, and I'd like to address this question, as I said before, using the causal inference framework. So here are the projects I have been involved in since a couple of years, and I'm still working on these kind of questions. I'd like to give you some sort of flavor of the problems we're looking at. This is a problem on flowering of Arabidopsis thaliana. This is a very convenient model plant. It's cheap, it's easy to plant. There's a phenotype, a response variable of interest. I denote it by Y. It's the days it takes until the plant is flowering. And the general goal here is to produce fast-growing plants and eventually fast-growing crop. We have many covariates. I denote it as covariates. I denote it by X. And this is the gene expression profile of the plant. So we measure more than 20,000 gene expressions for such a plant. And the question is, again, the same question. Can I infer or predict the effect of knocking out, here is the single gene, on the phenotype of interest? The phenotype of interest, the response variable is how many days it takes until the plant is flowering. So what we did, we used the statistical approach. We had only 47 observational data points, so it's a very high-dimensional problem. P is much, much larger than N. So you come up with a list, you chop off the list, and we actually validated the list. We validated the top hits. We were doing randomized experiments with my collaborator, and there was, I would say, some success. So there was actually, or we think there was information in the observational data, and we could exploit it to a certain extent. We also worked on yeast, gene expression of yeast, and this is a similar problem. It's kind of the multivariate version of my plant example. So here I have gene expressions from more than 5,000 genes. And I have a first phenotype of interest, a first response variable, which is just the expression, the activity of the first genes. And the covariates, the X's, are just the expression of all other genes. Again, I can go on. I have a second phenotype of interest. Y is the expression of the second gene, and the covariates are the expression of all other 5,359 genes, and so on and so forth. And the question is again the same. Can we infer or predict the effect of a single gene knockdown, the effect on all other genes? Okay. So we worked on that a while ago. We published that, and so I think it was quite a nice result, and I have some criticism to that today. So I remind you again what we have. We have a bit more than 5,000 genes involved. We also have 231 intervention experiments, so gene knockdown experiments. So thanks to those, we actually know what happens. So a gene was knocked out, and we can just check what was the effect on all other genes. And the total number of intervention effects is a bit more than 1 million. So thanks to these intervention experiments, we know the ground truth, at least in good approximation. The goal, again, was predicting these intervention experiments. So you put them aside and you try to predict them from observational data alone. We had 63 observational data points. That was just wild-type yeast. You predict with some sort of a causal inference machinery. And then you look at an ROC-type plot. So here are the number of false positive predictions. Here are the number of true positive predictions, of true hits. You see here, maybe you don't see it very well, but here is a fine dotted line. This is random guessing. These are regression techniques. This is the lasso, elastic net, and here is a causal inference technique, which seems to do quite a bit better than random guessing and in regression. It was a good finding, we thought. Some criticisms apply. I think this is a very hard problem. One of the criticisms is the finding is maybe not very robust. It depends in an unpleasant way how we validate the truth. That's a bit of difficulty here. Another criticism is, well, it's kind of old data. It was publicly available data, that was good, but we didn't know these people who published the data, so we didn't actually have the collaborator here. I think this is really not very nice. And we didn't use the interventional data for training, so we just used observational data and tried to predict the interventions. Okay, I'm still interested in this yeast knockout problem, and we think we have now a new and a better attempt. This will not be the last thing. I think we're making progress, maybe slowly, towards better solutions, but we have a new and better attempt for the same problem. The problem is, again, single gene knockdown in yeast. We measure genome-wide expression. We have observational and interventional data, and we have nice collaborators. That's good. This is Frank Holstege. This is Patrick Cameron, he's senior scientist. Holstege is a well-known, renowned scientist in the Netherlands who is very good at these gene knockout experiments. We have data from modern technology. The data is also publicly available. They published it last year in Cell. And we also come with a new approach. And this is where Jonas and Nikolai have been heavily involved and contributed very much. The approach is quite different what we've heard so far. I also try to do some sort of causal inference, but we use something else. We use an invariance principle. I try to explain that. And we try to take advantage that we may have heterogeneous data, exploiting an aspect of big data. I think at least some big data applications, they come in heterogeneous batches, and maybe this is an advantage for causal inference. And our approach, because we take a very different route, allows for statistical confidence statements, which is kind of nice as well. Okay, so we call it causal inference using invariant prediction. And there is somehow the main take-home message is here, and then I can finish. The main message is the causal structure, the causal components, they remain the same for different subpopulations or across different experimental settings. Okay, that's in a way a very key theme of my talk. The causal structure, the causal components, they remain invariant over various different experimental conditions, while the non-causal components, they can change across the subpopulation, and thus the idea is, well, take advantage of that, look for stability, for invariance of structures among different subpopulations. Okay? So if this is indeed true, then this is quite plausible to do, right? Then you just simply check over many different experimental settings whether you find structure which is the same, and then that will be the causal structure. Okay, let's make this a bit more concrete. The goal is to find causal variables or causal components among a p-dimensional predictor variable x, so that was my gene expression profile in the example, and I have a specific response variable y in mind. Like in the plant example, the days it takes until the plant is flowering. The data which we have is pairs xe, ye, and this comes from a distribution fe, and little e is an experimental setting, and script e here is the space of experimental settings. Okay? So this is what I call heterogeneous data. I know from which experimental setting the data is coming from. That's an assumption. We have different environments, different experiments from little e in script e. And as I mentioned before, I think this is at least an aspect of big data. Okay, so here it is again, the data, xe, ye, from a distribution fe, and that changes for different experimental settings. For example, this script e could be encoded just with two numbers. Equal 1 would encode, say, observational data, and equal 2 would encode all potentially unspecific interventional data. So in my knockout yeast example, all observational data is experimental setting 1, and all kind of interventional manipulation data is experimental setting 2. And you can go on and so on. I mean, script e equals 1, 2 could encode observational data 1, and maybe a specific intervention that's encoded by 2. You can have 3 encoding repeated data from a first specific intervention, a second specific intervention, and maybe all other unspecific interventions would be encoded by 3, and so on and so forth. Okay, so what's different from maybe the usual causal inference thing is we have a bit more information. We have access to more than, say, observational data only. It's very important that I have different experimental settings. So I assume here a setting with, for example, observational and potentially unspecified interventional data. This is realistic in many applications. So in biology, this is very realistic because people do have observational data and they do have perturbation experimental data, so this is available. Okay, so let's try to make it a bit more technical and mathematical, maybe not too much, but I'd like to show you a bit what's behind this machinery. I assume here a linear model setting that corresponds then to a linear structural equation model that's not crucial but makes the things much easier. So I have here an assumption, and I make it an assumption, and then I prove somehow that the assumption holds in some sort of more classical models. It's an assumption on invariance of causal linear predictions, and so it reads as follows. There exists a true vector, a regression vector, I denote it by gamma star. I call it the causal coefficients, such that, and so here is a regression problem. This is a linear model. Ye is xe, y is the response, x is the predictor. It has a regression coefficient, gamma star, and an error term. And the point is, gamma star is the same across all experimental settings. Okay, there exists such a vector gamma star. S star is the support of the gamma star. So these are all the components where gamma star is different from 0. So these are the variables whose regression coefficient is different from 0, and these are the causal variables, the causal predictors. And the epsilon here is the error term. It has to be independent of xs star. That's kind of the usual assumption. The error distribution is also the same across all experimental settings. Okay, so the message is here, the causal coefficients and the causal variables, the causal predictors, are stable across experimental settings. And people who maybe have thought about causality or things in that direction maybe think, okay, this is kind of intuitively meaningful. The causal system is really the stable system. And, well, whether you find it meaningful or not, I'll try to convince you a bit more and make it a bit more rigorous. Okay. So it's invariance. I think this is a nice and beautiful idea. It's an important mathematical and also scientific concept. Okay, let's make it a bit more rigorous. So this assumption which I make, is this actually something which we can connect to classical causal machinery, causal theory? And the answer is yes. So here's again the assumption. There exists this regression parameter gamma star, which is the same across all experimental settings, and the causal variables are my S star. So we prove this assumption for linear Gaussian structural equation models. That's kind of natural. This is a linear model, so we look then later at linear Gaussian structural equation models. And the result will be this gamma star, in fact, equals the usual direct causal effect in this linear structural equation model. So in other words, if you go the standard route with graphical models, you have your direct effects in a structural equation model, you can find it through this invariance property across different experimental settings. Of course, you need assumptions. It doesn't go without assumptions, that's clear. Roughly assuming is if there are no interventions, so if I manipulate, I don't manipulate on the y, on the response variable of interest. That's forbidden, but that's maybe kind of plausible. So in my plant example, I only manipulate the genes, but I do not manipulate directly the time it takes until the plant is flowering. Okay. And the second thing is gamma star and the error distribution, they do not change under the manipulations. That's kind of autonomous structural equation modeling. Also there, when you do a do intervention, the parameters do not change except that equation where you do the manipulation. Okay, so of course we face here also issues of identifiability. That's the same story or a related story. Just to make the point clear, if you have two variables, they're say jointly Gaussian, I have an x and a y, nobody can tell whether x causes y or y causes x. And that's not possible from observational data alone. I want to just show with that slide identifiability issues exists with this invariance approach as well. So let's talk a bit about this identifiability. And that's a bit more technical, and then I show applications a bit later. There might be many sets and many parameters. So this gamma is this regression parameter, S are the variables. There might be many of those who satisfy this invariance assumption. So what we do is we look at a hypothesis, take a gamma, take an S, and these are candidates where it is true. So this just means this is a gamma and an S where the invariance assumption holds. And I call S, comma, gamma, these are plausible causal variables. These are not the true ones. These are candidates to be causal variables and causal coefficients. Okay, so this is a hypothesis which you can test statistically. We'll come to that. Then you can get rid of the gamma. You read or you set up another hypothesis which is called, well, there exists such a gamma, that S gamma are plausible pairs such that the invariance assumption holds. And we call S a plausible causal set of predictors. So if that hypothesis holds, S are potentially causal variables. So what can you identify? And this is kind of plausible. So you look at all S which satisfy the invariance. There may be many variables, S, which satisfy that. And then you take the intersection of those, just the stuff which is in the intersection. So you take the intersection of all the plausible causal predictors, call it S script D, and that's actually what you can identify from the method and from the data. So we take the intersection of all plausible causal predictors, and we name that this is the identifiable causal predictors under script E. Script E encodes the experimental settings we're doing. Okay, so the point is, if you do that, and this goes a bit quickly, but it's not difficult to see, the SE, this identifiable stuff, must be a subset of this causal variable set. Okay, if there's a set of causal variables, this identifiable stuff is a subset. So if I find a variable here, I know it must be a causal variable. And this is very key. It's also key to obtain confidence bounds for causal predictors. This is another interesting point, I think, and we don't have the complete answers what we can do with this. But by definition, it's also easy to see what can you identify if you have some sort of experimental settings E1. Now you might have even more heterogeneity, more experimental settings E2, and what happens is the set grows. So with more interventions, more heterogeneity, more diversity, you can identify more. Okay, that's kind of plausible because you look for stability across the experimental settings. If you have more experimental settings, you can identify more. That's good. So what happens here is actually the identifiable set of causal predictors, it grows as the number of experimental settings grows. And that's nice. And the only question which remains is, in some sense, when is S script D? What you can identify, when is it the set of causal variables? And now we proved that for a certain model. In general, we don't know, but for certain models, we can prove that. And one setting is linear Gaussian structural equation models. We've seen them, I think, in the morning. So I have variables x1, xp, and the variable xp plus 1 is my y, my response. I have a linear structural equation model. I have Gaussian errors. And now I need to briefly talk what kind of interventions, what kind of experimental settings are we looking at to prove that SE is S star. If we take classical do interventions, that's one possibility. So I make a do intervention at single variables. I can look at noise or soft interventions, though that means I scale or I shift the error distributions. Maybe E equals 1 is the observational setting, and for all other experimental settings, I scale my error distribution or I shift it. That's another sort of intervention. I can look at simultaneous noise interventions. This means everything is pooled into one other experimental setting. This is the example. Maybe I have observational data only, and all sort of interventional data is put into another experimental setting, E equals 2. So under these kind of manipulations, you can prove the theorem, and the theorem reads, indeed, SE, what you can identify from this method, equals S star. These are the causal variables in the causal DAG in the linear structural equation model. Of course, these are assumptions. You have a causal DAG, you have a linear structural equation model, and if you ask the question, can you find the parents of Y, the answer is yes, you can do under these conditions, and these are the kind of interventions, manipulations I just described. Either under do interventions, under soft interventions, or under these simultaneous interventions. What's not so nice here so far is I need here to intervene at every variable here as well. Here it's not the case. One can relax this a bit. Okay. So this is one thing I think it's worth pointing out again. Let's go back to this. You can ask the question, where is it? This one. Is this a good principle? And I try to argue, yes, it's a reasonable principle, at least in linear structural equation models. Under some sort of type of interventions, you can prove that it matches back the classical causal machinery. Okay, so we can also say something on confidence statements, confidence intervals. This is maybe a bit technical, and I think maybe I skipped most of that. The main idea is what you have to do is you have to do a statistical test. Namely, you check for a set S whether it is a set of plausible causal variables. And what you have to do for that in concrete action, so you test constancy of the regression parameter and its residual errors across experimental setting. So you can do that, you can run a statistical test, you can test that hypothesis. So if S is a plausible predictor, you can go on, you can look at these variables from the set S, and then all what you have to do is to construct a classical confidence interval in a regression. So that's easy. So the two tools you need is classical confidence interval in the regression and a statistical test, and you're done. So what do you get? You get a confidence set for the causal parameter for gamma star. I denote it by gamma hat script D, depends always on your experimental setting, and you get a confidence set for S star, the causal variables, and you denote it by S hat D. What can we say with that? So here's another theorem. You make assumptions, you need assumptions. The assumption is the model is correct, you can do correct hypothesis testing, correct confidence interval construction, that's easy. And then you have the statement that the true causal parameter must be in this set gamma hat D with high probability. And maybe the second one is even more interesting. You have kind of a set S hat E, and you know you can construct it, and you know it must be a subset of S star. These are the causal variables, and that holds with high probability. So if I see a variable here in this S hat E, say the third gene, I know with high probability it's a causal gene. These are only bounds, you're on the safe side, and the red stuff I find very important and also very convenient in practice. The kind of method, I skip the details, but the method does not require that you need to specify what is identifiable and what is not identifiable. It automatically does it for you. If an effect is not identifiable, I get an infinite confidence interval, or the variable will not be in this set SC. So the method automatically deals with identifiability issue. You can just run it, you get a set S hat D. If the model is correct, of course it's not correct in practice, but if it's a good approximation, hopefully you get a good confidence statement. So I think this is one of the first results, or maybe even the first one on statistical confidence for causal predictions when you actually need to estimate the structure. You could do that by estimating the graph, and then having an estimated graph, make confidence statements there, and then come to the coefficients. But that's a very tricky route. This is much more direct and much easier to do. Empirical results, well, you can run simulations, of course. We did that also a bit to see how it performs. These are 100 different scenarios, 1,000 data sets per scenario. We only look at 2 experimental settings. Observational and interventional data in the 2 settings are the same. They range between 100 and 500. The dimension of the problem is between 5 and 40. And so here is the power, and here is the type 1 error control. So this is the success probability. With what probability do you get a true causal variable? Here is this invariant prediction method. Here is Lingam, another method. This is greedy interventional equivalence search. This is greedy equivalence search. This is regression. This is marginal correlation. And what you see is the method is not that bad in terms of power, but other methods are as powerful as this invariant prediction. If it comes to type 1 error control, this is family-wise error rate, the probability for at least one false positive. This invariant prediction method, which is aiming at 0.05 family-wise error rate, does very well in controlling the type 1 error, and the others do not. The others, of course, don't claim that they do it. But in fact, the invariant prediction indeed is controlling type 1 error quite well. So let's look at the gene perturbation experiment. So this is this Cameron et al. Data with Frank Holstege as the group leader. Genome-wide expressions in yeast. We have a bit more than 6,000 genes involved. We have 160 observational samples of wild type. It's quite a lot. 160 observational wild type genes is a lot, and we have 1,479 interventional samples that people did where they did knock out single gene deletions. So we run the method in the easiest mode. We just take 2 experimental settings. One is observational, and the other one is pooling all the interventional into one experimental setting. This is very crude, but we just thought this is maybe a good idea. Let's try it out. We use training test set division. For training the method, we use all observational data and 2/3 of the interventional data, and we try to predict the remaining 1/3, and then you do it randomly again and again. Okay, so then we have also a significance level. We try to control at 0.01, so a very, very stringent significance level, or 0.99 confidence, and then we can see what happens. So we found 8 genes with this method. The 8 genes turn out to be significant. And if you look whether they are true hits, among the 8, 6 are true hits. You need to define the truths. That's a bit tricky. But you have intervention experiments. You do see how they react if you intervene on one gene. What is the effect on other genes? If there's a large change, we call it a truth. So from the 8 which the method gives us, 6 are true hits. And this is the performance of other methods. This is IDA, this is greedy interventional equivalent search. So our invariant prediction method has most power, and it should exhibit good control against type 1 error. So this is another plot, what happened with this example. So on the x-axis, you see the number of predictions, and on the y-axis, you see the number of true predictions. And so you see the line here. This would be perfect. So if you have a method where every prediction you make is a true one, you would go up like this, so you go as steep as possible. That's good. This invariant prediction method is the orange one. It goes like that. That's a version of it with hidden variables. We can do that a bit as well. This goes like this. This here is PC IDA. This is the PC algorithm. And the bars here is kind of the 95% confidence region of random guessing. So PC is doing slightly better in random guessing. This other stuff is giving much better results. So this is a bit a more detailed view. Maybe I'll skip that and come to concluding thoughts. So I think there is some sort of robustness here, and because the main requirement is only the invariance. I only require some sort of invariance of a parameter or a set of variables across experimental settings. And this is not that a complicated condition in a way. Of course, we can only use that because we have the advantage of different experimental settings. We have shown that this kind of requirement actually coincides with the causality concept in structural equation models under various notions, at least, of interventions. We can also show it for some sort of hidden variable models. This is still in progress. But we kind of think the invariance assumption is maybe a rather robust assumption. We kind of don't know, it's a bit speculation, but it's some sort of an easy assumption, and maybe this is part of the reason why it performs well. We can come up with statistical confidence statements. That's essential, I think, for improving replicability. I have a plot here which needs time to load. Okay, here it is. This is purely exploratory. So what you see in the first row here is from observational data. And in this plot, every point is a pairwise correlation between gene J and gene K. Okay? And X and Y axis are two different data sets. So this is the Hughes data set, this is the Cameron data set. So this observational correlation of pairwise gene correlations, and you see there is no generalization from one data set to the other. There's no dependence. It's just exploratory. Here's with other data sets from the Hughes to another one, from the Cameron to the other one, and there's not much you can see. If you look at interventional data, so you have a gene J, you make an intervention, you look at its effect on a gene K. Okay, you can measure that effect, you quantify it as a number, it's a pair. So a point is a pair, and then I have this for a Hughes data set and the Cameron data set. And now what you see here is that there is something going on, some sort of dependence on the diagonal. This is the change of the intervention, this is the absolute change, and this is not just uncorrelated. You see some sort of dependence. So what that tells us is somehow in the interventional data, across these experimental settings, there is much more information which remains stable from one data set to another one. So due to robustness and benefit of heterogeneous data, maybe we made some progress towards more confirmatory causal inference. This is very ambitious, I think. If it isn't confirmatory, it's potentially useful for prioritization. You can come up with a list, and then you can run experimental validations according to your list. Simple organisms in biology are ideal for pursuing this, so I'm lucky I work with a plant biotechnologist, so we can actually run some of these experiments. This is in a way the take-home message. Causal components remain the same for different subpopulations over different experimental settings, and that explains one part of my title: we should really exploit the power of heterogeneity in big data. Thank you.
Good on time. I think we have time for one or two questions.
Could you say a word about the hidden version of your algorithm? You had a version that said it dealt with hidden things.
The hidden thing?
Yeah.
I need the slide again. So here's the model. So maybe look at it this way. This is my y, and my x, my predictor variable, is partitioned in a set C and E. C are the causes, E are the other variables. I don't know what C and E are, and so this is the intervention variable. This tells me what kind of intervention, what experimental setting I do. and this is the hidden variable. So the hidden variable goes to y, to the response, to c, to e, so c and e is x, but for example, the intervention doesn't go directly to y. So that's, in that model, we can also make identifiability statements. So where are you? I don't see you anymore. Okay. Does that answer the question? Okay.
So question, so you need both the intervention...
I can say it to me.
So you need both the interventional and the observational data to do this?
The question is whether I need both observational and interventional data, and the answer is yes. So, I mean, this kind of technique, it's kind of easier. I don't need to find graphs or Markov equivalence classes of graphs. That's very hard, very difficult, and the price to pay is exactly this. So we have more information. So we have at least 2 experimental settings. If I only have 1 experimental setting, only observational data, I'm dead. I cannot do anything.
And in the example you showed, I don't know what was the microorganism, but you had something like 6,000 genes,
Yep.
1,600 were knocked out. You had intervention.
Yep. So I show it again. So he asked about the example, what it actually was. I show it again. So I have 160 observational data points. This is my experimental setting encoded by 1. I have 1,479 other measurements, and this is what I put in my experimental setting too. Actually, I only use 2/3 of that because I want to predict the remaining third. But that's the idea. Just.
And do you have any sense for if you had much less interventional data, how much the performance would be great?
Okay, so I think he points at the open problem. One could, of course, I could do here across 1,480 experimental settings, right? The observational and all others. But I only have 1 data point per experimental setting, so that's not a good idea. So I need to have some sort of a trade-off between sample size and grouping. And this is kind of open how you do that.
All right, well, thank you very much. That's terrific. Okay, a few announcements. First of all, for those who missed the earlier announcement, we have 2 missing speakers tomorrow. So Michael Horowitz is going to start things off at 8:40. Breakfast will still start at 7 for those who come. And we will end a little bit early at the end of the day with a question and answer period that Jennifer Hill will run. Right now, we're going to go outside to the reception. You have to get back in here for the public lecture. Do we have a public lecturer? Is he here? We're hoping to have a public lecture. There was a delayed flight, and we're hoping he will arrive. So we're planning on it. So you have to be back in here by 6, and there's going to be a roped-off section for the speakers here in the front because there may be a big crowd. So the speakers should come up in the front. Be back in here by 6. Take your seats.
Please take all your belongings with you. The public will be coming in and seating in the back. Take all your belongings. The whole front lower part of the auditorium will be reserved for all of you.